All right, just started this recording. Today we're doing recommendation engines, super exciting. I think I've mentioned like a few times, this is my favorite part of the program, my favorite like one topic. If y'all are interested, this coming Wednesday, I'm actually presenting this as a workshop for Flatiron School, which honestly will be exactly the same material. But if y'all are interested, if anyone's based in New York, I'm actually presenting it in person. I'll send out the invite links or the event links to those. It's going to be both a webinar and also an in-person event at the same time. So if you're interested, that will be there. I'll send out those links later today. But cool, recommendation engines is the first of the 4 project topics for this phase. So yeah, today we're doing recommendation engines. Next week it's going to be 2 time series study groups followed by 2 NLP study groups. And then the following week is all going to be neural networks. And that will be, that's insane, but that will be the end of our curriculum material. But yeah, any questions that y'all have during this time, feel free to let me know. In terms of what we're talking about today, we're going to talk about 3 different kinds of recommendation engines, explain the concepts behind each kind, and also pros and cons of different engines and when to use which. So to start, the 3 main types of recommendation engines are non-personalized, content-based, and collaborative filtering. So just really quickly, non-personalized is not machine learning, it's just Python work, or you can just, by default give recommendations. I'll talk about that more in a little bit. Content-based, I won't talk in depth about the algorithms because they're actually very similar to algorithms that we've been talking about in like beginning of the week as well as last phase. The main algorithm we're going to focus on today is a collaborative filtering algorithm known as SVD. Not to be confused with SVD, the math that was used behind PCA. I'll explain more about that in a little bit, but that is the main algorithm we're going to focus on. It's called SVD. It's actually it's the algorithm that Netflix kind of uses. So it's obvious why we need recommendation engines. I feel like now with everything search optimized as well as marketing, ads, recommendation engines are super important. Some examples, I feel like I don't have to talk about examples, but you have the typical like Netflix, Spotify, even Google search results now have recommendation engines built into them. My favorite recommendation engines are like the Facebook and Instagram ads. I feel like they are annoyingly well curated to what I want to buy. Okay, but to start, the simplest one would be non-personalized recommendation engines. So several ways that you can go about it. The whole idea behind non-personalized recommendations is that they are not personalized. Just everyone gets the same recommendations. So different strategies of doing non-personalized recommendations, top rated items, maybe giving the most bought, watched, or consumed items. This is an example of YouTube. If you're not already, if you don't already have a YouTube account, this is what they show you. Basically whatever's most trending. Also, you can push out the items that will give companies the highest ROI. A really quick pro is it's so easy to make recommendations for people, right? Everyone just gets the same recommendations. However, is it the most effective? Some might argue because it's not the most personalized. No, it's not as effective. However, by giving non-personalized recommendations, it can actually be used as an entry point to gain more data, right? If you think about it from that standpoint, if you're first giving people like 5 trending videos over here, you can start to gain information based on which one of these 5 people click. So if you are just starting out as maybe like a new business or a new platform and you want to start garnering data, it can be helpful to just start with a low cost, easy to implement recommendation engine and then slowly build up from there. So I don't think I have to go very in depth into this. You get to basically decide what you want to recommend to people based on your data set. All right, so next we have content-based recommendation engines. Basically, the idea of content-based recommendation engines is it makes recommendations based on an item's features. Therefore, it's content-based. So a lot of models that we already know can do this. As an example, we're going to use movies. So let's just say you have data that looks like this. you have a bunch of movies and a bunch of different attributes. So you have genre, actor, director, year, IMDb rating, Rotten Tomato score, so on and so forth. Very, very similar to our phase 1 project. With data like this, you can build a content-based recommendation engine, and the strategies that you decide to use to create these content-based recommendation engines, really up to you. So it really does depend on exactly the kind of data that you have, but some very, very simple to implement recommendation engines. The first one would be nearest neighbors recommendation. So not so much of a classifier, but literally, let's just say the first movie I watch on Netflix is my favorite movie. I don't know. What's a movie? Titanic? I don't know. I actually haven't seen Titanic myself. But let's say I watch Titanic on Netflix and I love Titanic. All Netflix has to do is figure out what movies are most similar to Titanic based on these features and just recommend those other movies. So that's like a really, really quick way to generate recommendations, just based on what you know a user likes, find things that are similar to that, maybe by computing, distance metrics, nearest neighbors. Not just that, kind of similarly, you can also cluster items together. So again, with movies, you can, one, simply filter by genre and then recommend things of the same genre. But if you want to go a level up from that, you can cluster movies or your whatever items based on all of their features. So maybe you say, okay, I want to have like 20 movie clusters, of which I can pick and choose movies to recommend to a user who maybe likes one movie in one specific cluster. Other than that, you can also do classification algorithms if you have that kind of data. So for example, let's just say you have the movie watch history of a specific user, and you have, their 1 to 5 star ratings of all of the movies that they've watched. And there are actually a bunch of websites that curate this information. If you have that information, you can kind of build a classification or regression algorithm to try and predict the predicted rating of a movie based on its features, based on the movies that this person has watched in the past. So yes, I know I'm going through these really, really quickly, but these are all ways that you can make use of data like this to create content-based recommendation engines. Sweet. On that note, we can talk really quickly about similarity metrics. So we talked about similarity metrics when we talked about k-nearest neighbors. We talked about Euclidean distance, Manhattan distance, and when Minkowski's distance, which is all extensions of Euclidean distance. There are a couple other distance metrics that are used. Jacquard index, which is basically a ratio of the intercept and the intercept versus the not complement, what's the union, intercept versus union of things that people like and don't like. Cosine similarity is basically if every item is represented by a vector, what is the distance or what is the angle between their vectors? That's also a measure of similarity. Adjusted cosine similarity, pretty much the same thing as well. And also Pearson correlation. Now, interestingly, experimentally, based on a bunch of recommendation engines that have been built in the past, Pearson correlation happens to be the most effective distance metric, which is interesting because it's not really a distance metric, but it shows how overall tied or related different things are. But yeah, in any of those distance-based, content-based algorithms from before, you might employ different similarity metrics. Okay, so with content-based recommendation engines, I won't go any more into the algorithms and how you would use them specifically, because you just have to kind of reframe the way you've been thinking about the problems that we've already been thinking about. So let's talk about some pros and cons. So this is kind of funny. I once bought a plant on Amazon, but it died, but Amazon kept recommending plants to me. So this is, I think, one of the big cons of content-based recommendation engines. You start to get pigeonholed, right? Or what's the word? You start to get like typecast in a way. So for example, like if you only have watched like 5 horror movies on your Netflix account, all of your recommendations might be horror movies. One big pro of content-based recommendations is that you actually don't need too much user data for content-based recommendation engines, right? If you think about the way that we were talking about how we would implement any of the content-based recommendation strategies from before, which was over, I guess I don't have it listed out, like nearest neighbors, distance metrics, classification, regression, clustering. These are all based on features of the items, not really about the users, unless you're talking about like classification using the user ratings. You don't have to have as much user data in a content-based recommendation engine. So because of that, you don't have what's called the cold start problem. So the cold start problem is actually a pretty big issue when it comes to recommendation engines. And the cold start problem just means that if a brand new user starts using your app or your platform, how do you begin to make recommendations for them? Of course, with non-personalized recommendation engines, that's not an issue at all. With content-based recommendations is a lot less of an issue because maybe you just get a little bit of information, maybe even based on the person's like demographic or data that the platform can collect from you immediately. They can already start to make recommendations. But we'll see in a little bit, the next kind of recommendation engine, we do have a cold start problem. We'll get to that in a little bit, but cold start problem is something that actually a lot of new businesses have to think about, and content-based recommendation engines, that is a little bit less of a problem. Cool. All right, so next we're going to talk about collaborative filtering, and I'm going to start to speak a little bit slower because this is very, very important to understand, especially if you're very interested in the whole field of recommendation engines.
One quick question.
Oh,
Can you combine the first two? Like, can you combine the content-based and non-specific? Like, if you know that people are interested in a certain genre or like a type of movie, but then can you sort it by most popular or something like that?
Absolutely. Yeah, 100%. There are no rules to how you want to implement these things other than I think the main thing you're constrained by is how you want to code out these algorithms. But yeah, no, if you know that if you have like partial information about a person, you can definitely start to combine non-personalized and content-based recommendations for sure. Actually, there are ways to combine this one that I'm going to talk about in a little bit with the other two that we talked about, and I will mention those in a bit as well.
Great, thanks.
You're welcome. Okay, so before we get into the, and by the way, this algorithm we're going to talk about does employ gradient descent as well, which is super cool. But before we start talking about the algorithm itself, we have to think about the kind of data that goes into collaborative filtering. So before I talk about the concept of collaborative filtering, I want to talk about the utility matrix. So this is an example of a utility matrix. And what it does is it basically shows user ratings of different items. And this matrix is usually pretty sparse because if you think about it, not every user would have seen every movie on Netflix, right? So this is likely to be a very, very sparse matrix. So when it starts, it usually looks something more like this. Whereas you can see here, user 1 has only seen movie 1 and movie N. And this data in the middle, these are their ratings. So that means user 1 has rated movie 1 a 1, movie N a 3. If we go down to user number 7, user number 7 has only seen movie 2 and gave it a 4. So this is the kind of data type that you need for collaborative filtering because you want to make recommendations based on other people's patterns as well. I'll get more into that in a sec. The whole idea of collaborative filtering is with this utility matrix, you want to basically fill in those blanks and then recommend items with the highest prediction. So you start off like this. By the end of collaborative filtering, you end up with something like this, where every red number is a prediction of a movie that that user hasn't seen yet. And then you just recommend the highest one that they hadn't seen. So for example, for user 1, they hadn't seen movie number 2. The predicted rating is 4, so let's recommend that movie. For user M, who only saw movie N, you get a predicted rating of 4 for movie 2, so you're going to recommend that movie. So for this kind of recommendation engine, you're actually getting all of the predictions for all of the movie user combinations and then just spewing out the top recommended ones. So this data type, is important to note that this data is very, very different from the data of content-based, right? Because in content-based recommendation engines, that kind of data is very similar to the kind of data that we've already been seeing, right? It's kind of row by row. Every row is an item. And then your columns are your features. Whereas here, your columns are your movies are your columns, your users are your rows. Actually, if it's flipped, that actually doesn't make a big difference. You'll see why in a little bit, but just know that in this representation of data, your movies features or users features are actually not explicitly, they're not explicitly defined in your data. Cool, so this is called the utility matrix, important to remember. So the whole concept and idea of collaborative filtering is to recommend items based on the ratings of other users. If you want to think about it in an example way, let's say I like, I don't know, the Marvel movies. If I really like these superhero movies and you, my friend, also likes superhero movies, we know that we have that in common. So if I'm looking for a movie recommendation, I know to ask my friend who also likes the movie that I like, hey, what should I watch? And based on their recommendations, because we like the same thing, their recommendations are likely to be good recommendations for me. So it's just based on user similarities, based on ratings of other users. So there are a couple different ways to do collaborative filtering. There are memory-based methods as well as model-based methods. Model-based method is the one that we're mainly going to talk about, but we're also going to briefly talk about memory-based methods. Memory-based methods are good as baselines, and you'll sort of see why. The math is actually a lot simpler, but when we get to model-based, it scales up a lot faster. Okay, so to start, let's walk through within memory-based, there are two different ways to do memory-based collaborative filtering. We'll walk through each of these, but these two are kind of the same, just flipped on its axis. You'll see in a little bit. Okay, so we're gonna start with a very simple utility matrix, this one on the left over here. So for simplicity's sake, we just have one unknown value, and this does scale up, but we're just trying to figure out what this question mark predictive value is. What does user 1 likely rate item 3? Okay, so to get the recommendations for a user, first you have to get these user similarity values. This is called user-to-user collaborative filtering because you are banking on the similarities between users to start generating predictions. So what we're doing here is I'm using cosine similarity and I'm figuring out the level of similarity between user 1 and every other user. So I computed these in a Jupyter notebook way back when, but basically, if you're taking the similarity value between user 1 and user 2, 3, and 4, these are the similarity values. So basically, user 1 is most similar to user 4, least similar to user 2. After we have these, all we have to do is take a weighted average of their ratings for that specific item. So you can see here the 0.65, 0.76, and 0.83 correspond here in this equation over here. And then here we have 4, 5, and 4. This comes from what those users rated item 3, because this is the blank that we're trying to figure out. So once you do this multiplication, you just divide it by 2.24, which is the sum of these numbers. That's how you get a weighted average. And your prediction is 4.34. So user-to-user collaborative filtering has given us a prediction of user 1, item 3 to be 4.34. Questions about anything on this slide? Okay, awesome. So before we talk about other ways to do collaborative filtering, let's go through some pros and cons. So the obvious pro, it is highly personalized per user. However, it is computationally heavy. Of course, here it looked pretty simple because we only had a 4x4 utility matrix. But if you think about the fact that we have to compute user similarities between a target user and every other user and then take the weighted average, it can get computationally very heavy. So we'll see that these memory-based methods don't scale up very well. Also, there is the cold start problem. The cold start problem, which I talked about before. Imagine if user 1 was a brand new user and did not have any information at all. We wouldn't even be able to begin to compute the similarity between that user and every other user. So there is a very, very obvious cold start problem when it comes to collaborative filtering methods, which can be, I guess, bridged by using other methods of recommendation engines first. Okay, next there's also popularity bias. So because if you look at the way that this number is generated, it's by taking a weighted average of the other people's ratings for the same item. If this item was rated a 5 across the board, the math will work out that this recommendation will also be 5. So it is very, very prone to popularity bias just because it is building your prediction off of the rankings that other people have given the same item. So if you ever had an unpopular opinion about something, that would not be caught by collaborative filtering. Okay, so next we're going to talk about item-to-item collaborative filtering. Now this slide looks almost identical to the last one because it is almost identical to the last one. The main difference is in this other memory-based method of item-to-item, we're not computing similarities between users, but we're computing the similarities between items. And so as you see here, instead of doing the user similarity values, I have the item similarity values. So here, item 3, we're going to compare it to the other 3 items in the data set. Basically, it's most similar to item 4, least similar to item 1. The rest of the math, exactly the same. Here, we're taking the weighted average. Again, we have 0.78, 0.83, 0.87, multiplied by 4, 3, and 3. And that comes from 4, 3, and 3. Take the weighted average, you get a prediction of 3.31. Now, you're probably thinking that like 3.31 is a whole point different from what we got last time, which was 4.34. So depending on whether you do user to user or item to item, you can get very different values because of how they're computing similarities. Are you looking at similarities from a user axis or an item axis? You can get fairly different results. Cool. Questions at this point?
Would taking the average of both make sense, or is it like not because they're completely different comparisons?
You can totally take the average of both, but if you were to take the average of both, means you have to run both algorithms and then average the values, which ends up being way more computationally inefficient. We'll actually see the next method I'm going to talk about will give you a value in between these values. That's actually why the model-based method that I'm going to talk about next is the most used one.
Gotcha, thank you.
You're welcome. Anything else? Cool. All right, really quickly, let's talk about user to user versus item to item. So which is better? It really depends on your data, to be honest. It really depends on your data and also how you're deciding to track similarity. The more that you interact with these kinds of algorithms, I think the more you understand how it works for your data, for your context. So in general, though, experimentally, item to item has proven to be more effective because it is hard to predict users' unique tastes. What that means is it's harder to track the variation in user ratings onto items, but it's easier to see general trends within items, if that makes sense. Also, if you're looking at complexity, if you're trying to implement one of these algorithms and you have a different number of users and items, one is going to be more effective than the other. We haven't talked too much about complexity, but you can sort of think about it as running like a double for loop. If you have more users or more items, which will be more effective. So for M users and N items, this notation I actually won't really talk about, but neither is it super important for data science, but it is used in software engineering a lot because they care a lot more about efficiencies of algorithms. But basically, this tells you how efficient it is. And you want this number to be smaller, as small as possible. So the big O notation, which is what this is called, which is the measure of algorithmic complexity, for user to user is M squared N, because you're doing double computation on users because you're first picking out the similarity between one user and every other user, as well as taking those users' ratings. And then for item to item, it's the other way around. It's N squared. So which will be faster if you have more users than items? Item to item will be faster because you don't want to square the bigger number. Basically, that's one way to think about it. I talked about this earlier. Similarity metrics experimentally, Pearson correlation has just demonstrated to be the best one. No one knows why. It's just in practice when people have implemented algorithms, they have gotten best results out of Pearson correlation. Okay. So model-based collaborative filtering, and this is what I'm going to spend most of the time talking about. The algorithm is called singular value decomposition. Annoyingly, it is the same name as what we use to solve for PCA, but they're not the same process at all. So singular value decomposition, I'll talk about why this is different in a little bit, but it's just another way to fill in the utility matrix via matrix factorization. Now, SVD in PCA was actually done by doing the actual SVD process on your covariance matrix, right? If you decided to do the math on that in like one of the labs, that's pretty intense, honestly. But this actually does it via matrix factorization with gradient descent. We'll talk about that in a little bit. So in recommendation engines, how SVD works is you're breaking down the utility matrix into a user matrix and an item matrix. Now, a matrix does have rows and columns. So if you have a user matrix, the rows will be the users, but the columns will be latent features. I'll talk about what latent features are in a sec as well. And then you're going to do a gradient descent process using what's called alternating least squares to preserve the relationship between items and between users, which is what makes it parallelizable. I will call back this thing again as well later. It's very, very math heavy, but the best in class models do use some form of singular value decomposition. It's often tweaked a little bit, but it does end up performing very, very well. So for example, the Netflix competition was a recommendation competition that was run like in the late 2000s. Where, you know, given a bunch of users and movies, you're supposed to predict what their ratings are. Of course, you have a train set and you have a test set, but ratings from 1 to 5, some guy, his name is Simon, he used SVD. He basically conceptualized using SVD for recommendation engines. He ran SVD and predicted 1 through 5 to like a 97% accuracy. So that's pretty insane. So Netflix actually uses some derivative of this algorithm. So modified SVD for filtering in utility matrices. If you decided to go through the math for PCA, you will know that SVD takes one matrix and splits it up into 3 components. What those 3 components are, I kind of briefly mentioned it when we talked about PCA earlier this week. Not important to us, honestly. Modified SVD is because we are taking the utility matrix, and by the way, this is the same utility matrix that we played with in the memory-based methods. We're taking this matrix and we are splitting it into an item matrix and a user matrix. And the idea of matrix decomposition, which is what an SVD process is, matrix decomposition or matrix factorization, is you're expressing a matrix as the product of multiple smaller matrices. So technically, these 2 matrices, when we do the matrix multiplication back together, will give you this matrix. So we're going to split up this matrix into 2. So as I mentioned before, talking about latent features, when you split it up and you have an item matrix and a user matrix, each row here represents an item and each column here represents the user. But what are these values supposed to mean? Latent features basically can be thought of as PCA'd features, if that makes sense. So basically it's some vector representation of the item and the user. So to us, these numbers will have no meaning at all, but you can rest assured that embedded in these numbers are the relationships between items and between users, which I know is extremely abstract, but they're just a representation of the item and of the user. Questions about what we're about to do? Basically, the idea here. Oh, yes.
Each X is in both of the 2 latent features is representing both item and user.
So, well, a lot of, okay, so basically these two X's are a representation of item 1. These two X's are a representation of user 2.
Right, but I'm saying within each X, I think you.
No,
the
it
way you
doesn't
put-
have any, it doesn't, these X's have nothing to do with the user.
Okay,
I guess to some degree, a little bit, but let's go with no, just for simplicity's sake. It doesn't directly, but you'll see in a little bit how it does kind of embed a little bit of user information, but we'll go with no. These numbers do not represent users at all.
thank you.
You're welcome. Okay, all right, let's move on. So it is difficult to decompose a random matrix, especially if it's not square, it's very hard to break apart matrices in a way that will make sense. So therefore, where gradient descent comes into play is instead of trying to break down the utility matrix, we're going to recreate the utility matrix, which is kind of interesting. So this on the right is our original utility matrix. All the values are the same, and we need to figure out what this question mark value is. Instead of trying to take that matrix and split it into a user matrix and an item matrix, where mathematically there's also no way to quickly do that, we're going to try and just recreate it with a bunch of arbitrary user matrices and item matrices. So like with all gradient descent procedures, we're going to start with initial values. And what we're going to do is we're going to keep trying to recreate this utility matrix from the product of these two component item matrices, these two component item and user matrices. And the cost function that we're going to use here is the RMSE, which is, I guess, similar to what we did in regression. But this RMSE of 1.75 is basically each number here minus 2 squared, average of that. So 4 minus 2, 2 minus 2, 3 minus 2, the overall average error between the values, the item by item element wise error. And this matrix of 2's comes from us multiplying these initialized component matrices of 1's. So actually, if you work out the matrix multiplication for this, it actually works out to a 4x4 matrix of 2's if we initialize these all at once. Any questions about this? Okay. All right, so this is how we initialize, and our initial RMSE is at 1.75. And we want to get this.
Sorry,
Oh,
yeah, quick question. So that RMSE comes from the 2x2 matrix with the 2's, and then versus
yes.
the real one. Okay.
That's correct. Yeah. And I think this one isn't even counted. Like this 2 isn't even taken into account. But I mean, it's all relative, so it doesn't really matter. But yes, that's right. Cool. So we're basically, what we're going to do in the next process, we're going to try and figure out how can we change these values that will eventually change these values so that these values will match these values. All right. So step 1, let's just say I want to figure out a new value for this over here, this yellow X up here. Now, when I change this yellow X and I redo the matrix multiplication, it actually affects this entire top row. If matrix multiplication is still like not in your realm of understanding, it's completely fine. But just know that by changing this one X, or changing any one of these values in either this matrix or this matrix, it's going to affect an entire row or an entire column of your recreated utility matrix. So let's just say I'm going to try to figure out what the best value for this X is right now. When I do this matrix multiplication out, we'll keep it as an X so that we can solve for the unknown. When I do this matrix multiplication out, this becomes X plus 1's. So all we have to do now is figure out what the best value of X should be, such that the overall error between this row and this row is completely minimized. So how we're doing that, what this down here is, this, you see how there's 4, 2, 3, and 5. That corresponds to 4, 2, 3, and 5 over here. We're taking that minus the X plus 1 squared. We're basically taking the RMSE between 4, 2, 3, and 5 and this row of X plus 1's. Figuring out what the best value of X is, And you do that by taking a first derivative. Yeah, just do that by taking a first derivative. And I kind of solved it by hand as well. The best value of x here is 2.5. So the best value of x over here at this point of time is 2.5. So what happens when we change this to 2.5? This updates, this entire row updates to 3.5, and our RMSE has gone down from, was it 1.75 down to 1.58. Now, this process is going to be repeated over all of the values in both your item matrices and both your item matrix and your user matrix until your RMSE is as low as possible. Now, I mentioned the term parallelized before, back over here. It's parallelizable because it preserves the relationship between items and between users. Now, that is because every time you update a single value in one of these component matrices, it actually updates an entire row or an entire column of your recreated utility matrix. So just know that this recreated utility matrix is never going to completely match your original utility matrix. However, the relationship between all of the users and all of the items will be preserved in your recreated utility matrix. Whereas in this original utility matrix, it could be all random, who knows? All right, so after this process is done, it honestly doesn't even matter what values are here anymore. I actually solved this using the Python version and found all of these numbers. And I'll show you all how to implement in a sec as well. After running SVD, alternating least squares, which is the process of optimizing for 2.5 over there, that's called alternating least squares. After all of that, we end up with this recreated utility matrix and an RMSE of 1.15. So this RMSE of 1.15 says that on average, between my predictions, and actually all of these are predictions, and our original ratings, they're 1.15 off, which again, it kind of depends on context. Like if you're watching a movie, doesn't matter if it's like 5 stars versus 4 stars. I don't know, it depends on you. But now you can see that our RMSE has gone down to 1.75. And the predicted rating for that question mark is 3.7. Dimitri asked the question before, can you average the two? 3.7 happens to be not exactly right in between, but fairly in the middle of our values from before. And before we had 3.31 and 3.34. So naturally, because you're parallelizing it both ways, whereas here we're kind of parallelizing it only like on an item basis or on a user basis, you end up with a value that's in between the two values if you were to do user to user and item to item collaborative filtering. Cool. So with that, any questions? This is the end of the algorithm. Okay.
Do
So,
you determine
yeah.
the lowest RMSE just based on context, or is that built into the model somehow?
It is built into the model. Your RMSE will always go down because for example, if you were to change all 16 of these values, if you actually go back to here, 2.5 is not going to be the best value anymore. So it's going to keep repeating and repeating. It's probably going to like get better, but your amount of improvement is going to slow down pretty quickly. And I'll show you all in the implementation how you can like kind of adjust where to stop training your model, because it's pretty much going to keep doing it and like marginally decrease your RMSE by like very, very little.
Wouldn't it eventually just get it down to 0, but it would probably take years or something?
So it will actually never go to 0 because you want to preserve the parallel relationships. So in this recreated utility matrix, there are parallel relationships. However, in this utility matrix, there are not, if that makes sense. Because this utility matrix is created by a product of 2 component matrices, whereas this one is not. It's just random numbers based on user item ratings.
Oh, okay, I see. So it's kind of creating the relationships as it's doing it.
Yeah, it's sort of like trying to fit like a best fit line to your linear regression. You can never get RMSE of 0 overall.
Thank you.
You're welcome. All right, so this is a quick summary of all the models. We talked about 3 kinds of collaborative filtering, or 2 subsets of collaborative filtering, and within those two subsets, 3 different models. I want to talk about implementation now, because implementation is a little bit different from scikit-learn. So Surprise is the name of the library that you can use to implement SVD. Surprise stands for Simple Python Recommendation Engine System Engine. Basically, it has built-in similarity metrics, baseline methods, content-based systems, matrix factorization systems. And they do have a built-in data set, the movie lens 100K data set. So we're going to use that. So these are what we're going to import. These are our typical pandas NumPy. I do want to talk about data set and reader objects, because you do have to instantiate these things as well. I'll talk about that in a little bit. SVD is the model. Surprise has their own metrics library as well, or metrics methods. And then they also have their own train test split and cross-validation. One very important thing to remember is if you are using Surprise, don't import scikit-learn's train test split, because they will clash. So typically you don't end up using both libraries in the same project anyways. So just take note that you're importing it not as the same thing. Okay, so we're going to use this built-in data set to start. And this built-in data set, what's a little bit annoying about it is it's kind of opaque. So if I run this, I'm loading the 100K movie lens data set, do a train test split, and I'll show you all an example with real data in a little bit. The train set looks like an object like this, so you can't really look at it. But in terms of implementing the model, it's very, very similar to scikit-learn. Surprise is actually built off of scikit-learn to some degree. So first you instantiate the model, you want to fit it on your train set, test it on your test set. So same 3 steps that we've been working with last phase. This will take a little while because it's running, I think, 100K. Hopefully it doesn't take too long. There we go. And we just end up with an RMSE of 0.94. So on average, we are 0.94 stars away. I don't even know the context of this. I think this is like 1 to 5 stars. So 0.94 stars away between your predictions and your actual. Not too bad. And this is also on your test set, because this comes from predictions. If you want to use your collaborative filtering model, it's actually pretty neat. For this data set, the user and item IDs come as number strings. And so all you have to do is do svd.predict. You can get your user ID, give it your user ID, item ID. If there is a real rating that you want to compare it to, you can feed it in that. And it gives you your estimated rating of 4.25. Okay, so really, really quickly, those are the implementation steps, very similar to what we were doing with scikit-learn in the past. But now let's use some real data. This is going to be Yelp's data. And in the Yelp data set, they have a reviews data set basically, where you have user IDs, business IDs, and the number of stars the user rated the business. One good thing to note is that this is actually the utility matrix, but expressed in a more efficient format. If we take a look at the utility matrix from back here, this one, utility matrix. Okay, so this utility matrix, imagine if you had millions of users, millions of businesses, it would be kind of a waste of space to store all of these blank 0 values. So therefore, they express it as a sparse matrix type or coordinate. It's also called coordinate representation. So basically, it'll just be, okay, movie 1, user 1 is run. So you essentially only will need 3 columns of data. So thankfully, Surprise takes in the data this more efficient way, where you have user ID, business ID, stars. You can see that the first 5 business IDs at least are the same restaurant, or I don't know, the same business. So if you wanted to, you could recreate the utility matrix, but extremely inefficient use of space. So for recommendation system, let's just do a very, very quick EDA. Of course, you would do a more comprehensive one. But in this data set, we have almost 80,000 users with about 2,500 businesses. We can just do a very, very quick value counts. You can see that we have mostly 5-star reviews, followed by 4 stars. We have the least number of 2- and 3-star reviews. So good to know. You would also do this in a graph, probably. And then if we see how many times businesses have been rated, This business has been rated 1,694 times, and this is down here rated only 3 times. You can also do the same kind of EDA on your users as well to see how often, on average, your users are making ratings or leaving ratings. Okay, so this is the slightly new part where we have our reader objects and your data set objects. So first, the reader object. The reader object basically has you tell it what are the range of ratings. So it's kind of important that you check your EDA first to see what your range of ratings are. In this case, for Yelp, it's 1 to 5. You cannot go lower than 1. You cannot go more than 5. I know some data sets allow you to go to 0. Some data sets I've seen allow you to start at 0.5 and then you have 0.5 increments, but give it your min and your max. So here we're setting the reader, your rating scale within your reader to be 1 through 5. Next, what's pretty neat is that the dataset object from Surprise allows you to load your data from a data frame directly. So here, if you take a look at our Yelp dataset, which is over here, what is, I learned the hard way, really important is that you feed in your columns in the right order. So you have to feed it in through this order, and I'm just giving it my columns just in case. It has to correspond to user ID followed by item ID followed by the ratings. So I do that, and within load from DF, I also have to give it my reader object. So now that is done. The train test split, because you don't really have an X and a Y, you only have to feed it in your data, and the data has to have gone through your data set object. So once you've done that, you can see your train set is that train set object that we talked about. The test set, though, I think the test set, no, that's test set you can still see. So you can see that it's a list of tuples with the user ID, business ID, and the rating. Cool. So fitting and evaluating models. You also have grid search built into Surprise. Actually, let me pull up the documentation real quick. So I actually really like Surprise's documentation because I think it's very, very clear. But here you can see that in model selection, you can do a grid search. Here, parameter search, you can use grid search within their library. They also have not just SVD, but they have a lot of other different algorithms. So for example, KNN is actually item-to-item collaborative filtering. And there are also some variations on them, taking into account different things. So yeah, this one is the famous SVD algorithm. This is the one that we're going to use. As I mentioned, it was popularized by Simon Funk during the Netflix prize. So yeah, feel free to explore. If you're doing a recommendation system project, very similar to how the last project you're trying like 10 different models for classification, you could try all of these for recommendation engines. Okay, so back to this. Let's just fit this model. And I do want to talk about some of the hyperparameters. So while it's fitting, and epochs. So epochs is something that we'll talk more about when we get to neural networks. But in this scenario, epochs is basically how many times, let me go to this slide, how many times all the way around are they going to keep changing values? So if I were to do this process 16 times for each of these values, that's 1 epoch. When you do that a second time, 2 epochs over and over. So usually the more epochs you do, the closer you get to your low RMSE, but also if you do it too much, it's kind of redundant because you don't improve by very much after. So that's that. N factors is basically how many latent features you have. So n factors equal to 1 just means that this doesn't have 2 columns, it only has 1, and this will only have 1 row. So that's what n factors is. Typically, if you have more n factors or more latent factors, you're taking into account more granularity in the embedded information of the representation of the item or the user. That's what n factors is. I forget what biased is. I don't think that's super important, but this is learning rate and this is regularization. So you can introduce both of these into your model as well. And this is something that you can definitely tune as well.
So n factors just kind of makes the process longer, so it may be more accurate.
Yes, that's right. It makes it longer so that it may be more accurate, correct. Well, actually both epochs and factors does that.
Right.
In different ways, but yeah. Something that you can also tune for is if you like take into account how long it takes to train and test, that could be something that you use to decide what model to pick or what hyperparameters to pick. Okay, so next we'll make our predictions. Now, instead of doing dot predict, they do dot test on a test set. So here we have our predictions, and just to look at what predictions look like, this is what our predictions look like. Let me, oh, okay, I guess we can't do that. All right, so for our first 3 data points in our test set, it'll basically say, all right, this was the user, this was the item. These are the real values, and these are the predictions. So as you can see, not bad, right? This first one predicted 3.88 when it was 4, 3.84 when it was 4, and this one predicted 4 when it was a 3. So overall, not bad. And then you can also just get the RMSE and the mean average error, or mean absolute error, sorry, for your data set. So you can see the RMSE for this one is 1.3, MAE is 1.05. Up to you to decide in context whether that is good or not. And again, for making predictions, unfortunately, this data set has convoluted strings as the user and business ID, so we don't know what these are, but you can still make your predictions here. For this user, this item, this is the estimated rating. If you just want to change the numbers a little bit, you'll see that these will change. If you give an invalid user ID or business ID, like one that isn't in the data set, let me see if this works. Yeah, it'll actually give you a standard average rating. So see how this is 3.537. I believe if I keep changing this, they'll still be 3.537. So every time you give it like a user ID or business ID that isn't in your data set, it'll just give you the average rating by default. So it actually helps with errors, but pros and cons, you won't catch those errors. But yeah, what else there is, Surprise actually provides you with the code to get the top end recommendations for any user, which is one of the reasons why I really like Surprise. They actually give you this function straight up. And then also some resources. This is a really, really good book if you are interested in recommendation engines. Also, Surprise documentation. LightFM is another library. So Naomi earlier asked about combining some recommendation engines. So LightFM actually is a library that allows you to combine content-based and collaborative filtering recommendation engines, which is super, super cool. So how it works is it does collaborative filtering first and then re-weights your predictions based on the explicit item features or user features as well. If you had like user data, like where they're from, their age, things like that, you can actually incorporate that into your recommendation system as well, automatically using LightFM. So that's very cool. LightFM's documentation also links to a bunch of Jupyter notebooks that walk through how to use their library. So that's very nice. Also, I wrote my blogs from way back in the day were actually all on recommendation engines. So if you're interested, they're on Medium, but they're basically the same thing as what I'm talking about today. But yeah, that's recommendation engines. My favorite part of the curriculum, I'm not shy to say. So if anyone wants to talk about it, let me know. If you want to talk about anything else, you can also let me know. But yeah, any questions on this? All right. Well, if there are no questions, let me stop the recording.